Brain-computer interfaces, often referred to as BCIs, are innovative systems that establish a direct communication pathway between the brain and an external device, such as a computer or prosthetic limb. These interfaces enable individuals to interact with technology using only their brain activity, bypassing the need for traditional input methods like keyboards or touchscreens. By decoding neural signals, BCIs translate the user's intentions into commands that can control various devices or applications. This groundbreaking technology holds immense potential for revolutionizing fields such as healthcare, gaming, and assistive technology. One interesting fact about brain-computer interfaces is that they have been successfully used to help individuals with severe motor disabilities regain some level of independence. For example, researchers have developed BCIs that allow paralyzed individuals to control robotic arms or even communicate through text or speech synthesis. This remarkable capability not only enhances the quality of life for those with physical limitations, but also opens up new possibilities for human-machine interaction. In essence, brain-computer interfaces represent a bridge between the human brain and the digital world, offering a glimpse into a future where our thoughts can directly influence technology. As research in this field continues to advance, the potential applications of BCIs are expanding rapidly, paving the way for a more interconnected and accessible world. Brain-computer interfaces have found diverse applications across various fields, showcasing the versatility and potential of this technology. In the healthcare sector, BCIs have been instrumental in assisting individuals with motor disabilities. For instance, researchers have developed BCIs that enable paralyzed patients to control robotic arms with their thoughts, offering them a newfound sense of independence and mobility. These advancements have the potential to significantly improve the quality of life for those with physical limitations. Another fascinating application of BCIs is in the field of neurorehabilitation. By utilizing brain-computer interfaces, therapists can create personalized rehabilitation programs that target specific areas of the brain, aiding in the recovery process for patients recovering from strokes or traumatic brain injuries. BCIs have also made significant strides in the gaming industry, where they are being used to enhance the gaming experience and provide new ways of interaction. Gamers can now control characters and navigate virtual environments using their brain activity, adding an exciting dimension to gameplay. Moreover, BCIs have shown promise in the field of education by enabling students to interact with educational software and devices using their thoughts. This innovative approach not only enhances engagement, but also opens up new possibilities for personalized learning experiences. In addition to these practical applications, brain-computer interfaces have also been explored in the realm of art and creativity. Artists and musicians have used BCIs to create unique performances and installations that blur the lines between technology and human expression. By harnessing the power of brain signals, these creators can produce captivating works that challenge traditional notions of artistry. Overall, the current applications of brain-computer interfaces demonstrate the transformative potential of this technology across a wide range of domains, from healthcare and rehabilitation to gaming, education, and the arts. As research in this field continues to evolve, we can expect to see even more innovative uses of BCIs that push the boundaries of what is possible in human-machine interaction. Developing brain-computer interfaces presents a myriad of challenges that researchers and engineers must overcome to unlock the full potential of this technology. One of the primary challenges is the complexity of decoding and interpreting neural signals. The brain produces a vast amount of data through electrical impulses, and extracting meaningful information from this neural activity requires sophisticated algorithms and signal processing techniques. Researchers face the daunting task of developing accurate and reliable methods to translate these signals into actionable commands for external devices. Another significant challenge is the issue of signal variability among individuals. Each person's brain activity is unique, and factors such as age, health conditions, and electrode placement can affect the quality and consistency of neural signals. This variability poses a challenge in creating universal BCI systems that can be effectively used by a diverse range of users. Moreover, the invasive nature of some BCI technologies presents ethical and safety concerns. Implanting electrodes directly into the brain carries risks such as infection, tissue damage, and long-term compatibility issues. Balancing the potential benefits of invasive BCIs with the associated risks requires careful consideration and ethical oversight. Additionally, the scalability and affordability of BCI technology remain significant challenges. Developing cost-effective and user-friendly BCIs that can be widely adopted outside of research settings is crucial for realizing the widespread impact of this technology. Furthermore, ensuring data security and privacy in BCI systems is a pressing concern. As BCIs collect sensitive neural data from users, protecting this information from unauthorized access and misuse is paramount. Addressing these challenges requires interdisciplinary collaboration, innovative solutions, and a deep understanding of both neuroscience and engineering principles. Despite these obstacles, researchers are making remarkable progress in overcoming these challenges and advancing the field of brain-computer interfaces towards a future where seamless interaction between humans and machines is a reality. Advancements in brain-computer interface (BCI) technology have propelled this field into new frontiers, offering unprecedented opportunities for human-machine interaction. One of the key advancements in BCI technology is the development of non-invasive techniques that enable users to control devices using external sensors placed on the scalp. These non-invasive BCIs, such as electroencephalography (EEG) systems, have made significant strides in improving signal quality and accuracy, paving the way for more accessible and user-friendly BCI applications. Researchers have also made remarkable progress in enhancing the speed and efficiency of BCIs through the use of machine learning algorithms. By leveraging artificial intelligence and deep learning techniques, BCIs can now interpret neural signals more effectively, enabling faster and more precise control of external devices. This advancement has revolutionized the field of neuroprosthetics, allowing individuals with disabilities to interact with their environment in ways previously thought impossible. Another exciting development in BCI technology is the integration of virtual and augmented reality systems. By combining BCIs with immersive technologies, such as virtual reality headsets, users can experience rich and interactive virtual environments controlled solely by their brain activity. This fusion of BCI and virtual reality opens up new possibilities for gaming, education, and therapeutic applications, offering a glimpse into a future where the boundaries between the physical and digital worlds blur. Furthermore, researchers have made significant strides in miniaturizing BCI devices, making them more portable and discreet. Wearable BCIs, such as brain-sensing headbands and smart glasses, are now available, allowing users to seamlessly integrate BCI technology into their daily lives. These compact and lightweight devices offer a level of convenience and mobility that was previously unattainable, expanding the reach of BCI technology beyond the confines of the laboratory. One particularly fascinating advancement in BCI technology is the development of hybrid BCIs that combine multiple input modalities. By integrating brain signals with other physiological signals, such as eye movements or muscle activity, researchers have created hybrid BCIs that offer enhanced performance and reliability. These multimodal BCIs leverage the strengths of each input modality, resulting in more robust and versatile control interfaces. Moreover, advancements in neuroimaging techniques, such as functional magnetic resonance imaging, fMRI, and magnetoencephalography, MEG, have provided researchers with unprecedented insights into the workings of the brain. By combining BCI technology with advanced neuroimaging methods, scientists can now decode complex brain patterns and understand the neural mechanisms underlying human cognition and behavior. This synergy between BCI technology and neuroimaging holds immense promise for advancing our understanding of the brain and developing more sophisticated BCI systems. In conclusion, the advancements in brain-computer interface technology have propelled this field into a new era of innovation and discovery. From non-invasive techniques and machine learning algorithms to virtual reality integration and hybrid BCIs, researchers have made significant strides in enhancing the capabilities and accessibility of BCI technology. These advancements not only hold promise for improving the quality of life for individuals with disabilities, but also offer new avenues for human-machine interaction and cognitive enhancement. As research in this field continues to evolve, we can expect to see even more groundbreaking developments that push the boundaries of what is possible with brain-computer interfaces. Ethical considerations play a crucial role in the development and use of brain-computer interfaces, BCIs, raising important questions about privacy, autonomy, and consent. One key ethical concern is the potential misuse of neural data collected by BCIs. As these devices gather sensitive information about an individual's thoughts and intentions, there is a risk of this data being exploited or misused without the user's consent. Safeguarding the privacy and security of neural data is essential to ensure the ethical use of BCIs. Additionally, issues of autonomy and agency arise when considering the implications of using BCIs for decision-making and control. Questions about who has the right to access and interpret neural data, as well as the extent to which individuals can retain control over their own thoughts and actions, highlight the complex ethical dilemmas inherent in BCI technology. Moreover, the potential for cognitive enhancement through BCIs raises ethical questions about fairness and equality. As BCIs offer the possibility of enhancing cognitive abilities beyond natural limits, concerns about access, equity, and societal implications come to the forefront. Addressing these ethical considerations requires a thoughtful and multidisciplinary approach that prioritizes transparency, informed consent, and respect for individual autonomy. The future prospects of brain-computer interfaces, BCIs, hold immense promise for revolutionizing various aspects of human life. One exciting area of development is the use of BCIs for enhancing communication and interaction. Researchers are exploring ways to improve the speed and accuracy of neural decoding, enabling more seamless and natural communication between the brain and external devices. This advancement could have profound implications for individuals with speech or motor impairments, offering them new avenues for expression and connection. Another intriguing prospect is the integration of BCIs with artificial intelligence, AI systems. By combining the power of BCIs with AI algorithms, researchers aim to create intelligent interfaces that can anticipate user intentions and adapt in real time. This synergy between BCIs and AI has the potential to revolutionize human-machine interaction, enabling more intuitive and responsive technologies. Furthermore, the field of neuroprosthetics stands to benefit significantly from advancements in BCI technology. Researchers are working on developing more sophisticated prosthetic devices that can be controlled directly by the user's brain signals, mimicking natural limb movements with greater precision and dexterity. This could offer new hope for individuals with limb loss or paralysis, providing them with enhanced mobility and independence. Additionally, the future of BCIs holds promise for unlocking the mysteries of the human brain. As researchers delve deeper into the neural mechanisms underlying cognition and behavior, BCIs offer a unique window into the inner workings of the mind. By decoding complex brain patterns and understanding how thoughts are represented in the brain, scientists can gain valuable insights into human consciousness and perception. Overall, the future of brain-computer interfaces is filled with possibilities that have the potential to transform how we interact with technology, communicate with one another, and understand the complexities of the human brain. Brain-computer interfaces, BCIs, have the potential to have a profound impact on society, transforming the way we interact with technology and each other. One significant area where BCIs could make a difference is in healthcare. BCIs offer new possibilities for individuals with disabilities, allowing them to regain independence and improve their quality of life. For example, BCIs have been used to control robotic limbs, enabling paralyzed individuals to perform everyday tasks with greater ease. Additionally, BCIs hold promise for enhancing medical treatments and therapies by providing insights into brain function and neurological disorders. Another interesting aspect of BCIs is their potential to revolutionize education. By enabling students to interact with educational tools and devices using their thoughts, BCIs can create more engaging and personalized learning experiences. This technology could help individuals with learning disabilities or attention disorders by offering alternative methods of communication and expression. Furthermore, BCIs have the potential to reshape the gaming and entertainment industries. Gamers could experience more immersive and interactive gameplay by using BCIs to control characters and navigate virtual worlds. This innovation could open up new possibilities for virtual reality experiences and storytelling. Overall, the impact of BCIs on society is multifaceted, offering opportunities for empowerment, inclusion, and innovation across various domains. In conclusion, brain-computer interfaces, BCIs, represent a groundbreaking technology with vast potential to transform various aspects of society. From healthcare and education to gaming and entertainment, BCIs offer new opportunities for empowerment and innovation. By enabling individuals to interact with technology using only their brain activity, BCIs are revolutionizing human-machine interaction and opening up new possibilities for individuals with disabilities. The advancements in BCI technology, such as non-invasive techniques, machine learning algorithms, and virtual reality integration, are propelling this field into a new era of discovery and exploration. As researchers continue to push the boundaries of what is possible with BCIs, we can expect to see even more remarkable developments that enhance our understanding of the human brain and redefine how we engage with the digital world.